Hello and welcome to C Programming Zero to Neural Networks. In this part we are discussing files, we are covering files. In particular, files on a block storage device. We usually say files on a disk, but most people have NVMe drives or SSDs in the very least, and very few of us actually have spinning disks in our hard drives anymore. We use the more general term of block storage, so block storage files. What we're going to do is we're going to build a simple copy command using the system call rather than the user space fopen library function to learn a little bit about system calls and to just cover more C programming basically. We use files a lot, obviously. You'll have heard the Linux or the Unix paradigm that everything is a file. So everything's treated as a file. Devices are files. Network sockets are sort of handled as files. So everything is treated as a file. In particular, we're talking about block storage files in this part though, and as I said, we're going to make a simple copy command, which is the best place to start with learning about file handling in any programming, but in particular in C programming, and we need to handle a few errors and that kind of thing. So it should be an interesting part to go through. So first of all, where does a file live? Let's draw out a file system. So you've heard the term file system before. You know what a file system is. You've got NTFS on Windows and FAT, FAT 16 and 32. You've got on Linux, you've got EXT, EXT2, EXT3, EXT4, ZFS. We've got loads of file systems, haven't we? So what they generally all have in common is we have two parts to the file system. So when we format a block storage device to a particular file system, we do so in a particular way, conform with that file system, but they all work in basically the same way. So they have a section which contains matter, which contains metadata, and a section which contains the actual data. So what's the metadata? So metadata is things like file name, it is date created, permissions, and so on. Metadata, obviously, metadata about the file. And then in the data section, I've put data. We've got the actual file itself, which is not necessarily in one big continuous block. It could be spread over the disk like that, particularly if it's a big file. So we also, in our metadata, contain pointers to each part of the file. And this is how a file looks like on a file system. And we have the terminology of fragmentation, which I would imagine most people who have some knowledge of computers are aware of. The more a file is sort of spread out over the disk rather than a block, the more fragmented it is. It's fragmented. The less fragmented it is, the more in a continuous block it is. So we have these pointers. So this makes up a record of our file, and we call this, in Linux terminology, an inode. And then this is simply the data that it points to. So an inode, which you can consider to be short for information node. So maybe it stands for information. And I'm sure I've read in a book somewhere that Ken Thompson, who made Unix, who came up with most of this terminology, certainly the terminology of an inode. He actually can't remember why he called it an inode. So it's not really a definitive term calling it an information node, but it does kind of make sense. So I go with information node for inode. So on a Linux system, and you'll find the same thing in any operating system, because all operating systems have, when it deals with block storage, have file systems which all work in pretty much the same way. They just use slightly different formats and slightly different conventions. We have a metadata section, and then we have the actual data section. And the metadata section consists of records which contain the file information and which point to the data blocks of the actual file itself, so the file can be retrieved and loaded into memory and so forth. So let's, before we actually start programming, to go through the everything is a file paradigm on Linux. If we go to our dev directory, you'll see we've got all our devices here, one of which is a subdirectory called input. So let's go into that. And we've got a load of event 15, event 16, event 3, not very descriptive. If we go into our by path directory, we can see that we've actually got descriptive events. We've got keyboard, mouse, well down here we've got the actual main ones, keyboard, speaker, event, mouse, all these different sort of vaguely human readable input events. So these look like files, don't we? Because we can ls and we can see them as files. So let's cat. So we know what the cat application does, concatenate. It basically outputs the contents of a file to the standard out. So let's concatenate the contents of our keyboard to the standard out. Let's do that. As we type, we can see that file reading. That's live input coming from our keyboard, which is all sort of, I'd say it's scrambled, but these are attempts at rendering binary information. So this isn't really ASCII data coming in. These are keyboard events that need to be sort of parsed into actual key presses. So our keyboard exists in our operating system as a file, but it's not a block storage file, but we can open it with system calls like open, read and write. We can open that file and then we could build a keylogger, which is a good exercise to do. Actually, might cover that sometime. So we can build a hacking tool called a keylogger, which records every single key press and stores it in a file. And we can give the keylogger a really generic name like System Proc. so people wouldn't notice that it was some rogue process. So obviously if we call it hacking keylogger program, then it's going to show up in the processes and on top, isn't it? Anyway, that's another story for another time. Let's make our file copy program. Let's get started. So we're going to make a program. We're going to call it LPC. I've decided LCP, learning copy.c. And we're going to need quite a few library functions for this, but we're definitely going to need the standard input output library, and we're going to need to put an L there. We're going to need a main function, because we need a main function in every single C program, and we're going to return a 0 to the operating system by convention. So first of all, the first thing we need to cover, let's make sure everything compiles all right. We want our program we want to be able to supply an input file and an output file, don't we? That's how we want the program to work. So how do we do that? I've not actually covered this, but it is actually quite simple. So, although sanitizing user inputs is more complicated, very difficult, and if we have things like flags that we want to pass to a main function, then we get into a really complicated territory. We can end up with half of the program being just sort of parsing the inputs that we pass to a main function. So when I say this is pretty straightforward, it's pretty straightforward for what we're going to be doing here, because we're going to do it in the simplest way possible. So basically what we do, we need to have two parameters in our main function. So we're going to have int argc char star argv array, space there. So int argc stands for arg count. So this is the number of arguments that have been passed to the main function. And then char star argv array is an array of string literals, which are the actual argument values. It actually stands for argument vector, but you can think of it as standing for argument values as well. The logic works exactly the same. So let's make a for loop to demonstrate how this works. The best way to learn this is to see it in a for loop. C I++. So we're going to loop from 0 to arg count, and now count is the number of arguments that we've passed, as we've said. And what we're going to do is we're going to print out the argv string at position I. So well, you'll see how this works. So when we run this program now, we print out a single argument, which is the program name, which is always the first argument. I don't think I've put a new line. Let's put a new line, otherwise this is not going to look very good. So now if we run it with an argument, we print out the program name, and then the second argument is test, and then we can have test2, another test, and then just some random text. And this is a meta font. Have I randomly spammed some random key combination for latex by the looks of it or something? I have no idea what I've done there. What does that do? I have no idea. That's a mystery for another time. Anyway, so you get the idea with the argument. So test2, and then we'll print out our different arguments. And obviously we can now do input file, output file, and as long as we're putting in paths to actual files, then we can open those files, we can write to those files, we can do whatever we want with those files. So let us continue. So we need to sanitize this input. So we don't want to be able to supply a million files, do we? We want a limited functionality to this program. So let's get rid of that. We want a simple if in here, and we want to do if arg c is not equal to 3, and then we're going to end the program there. So we need to supply exactly 3 arguments: the program name, the input file, and the output file. Any deviation from that, this program is just going to end. And we may as well fprintf an error saying, shall we do a usage prompt, lcp input file output file, to prompt the user on how to use the program. Let's see how this works. Usage input file, if we supply 1 argument, no, it doesn't work. If we supply 2 arguments, the program works. Now we can do a lot more. I'm going to leave the handling arguments at that because we want to get onto files. But I would probably sanitize the case where we have the input file and the output file being exactly the same. We don't want to write to the output file, do we? We want to read in and out to the same file, if you know what I mean. It's not going to make much sense. But we'll leave that for now. When we build a more complicated program, we can do a more complicated argc, argv parameters. For now, this will do for our copy program. So what we want to do is we want to open a file, don't we? So this open system call, I think if I just open this, it opens the wrong one. Man to open. So our open system call, first we need to have this header file, fcntl.h, which stands for file control.h. So we need to include that to be able to use this open system call, and we need to supply the path name, flags, and then optional modes. And the flags are ORD only, which obviously stands for O read only, OWR only, which stands for O write only, and ORDWR, which stands for read write. So that we have 3 possible flags, and they're pretty self-explanatory. The reason there's an O underscore is because these are a bitwise OR, which I might explain at the end, or I might do an actual separate part on bitwise operators and bitwise ORs. We'll see how quickly we get through this. So open arg v1. We want to open our first file, and then we want to supply flags O underscore RD only, read only. That's how we want to open our first file. Now we need to save this into something. What we do is we do int fd equals file descriptor, this, and we can call it whatever we want. We can call it file. But FD is a pretty common terminology for it, because this is from the Linux kernel's perspective, a Unix kernel's perspective, we're dealing file descriptor. So this int isn't just a regular old number; it's a reference to an open file. The operating system itself maintains for every process a list of open file descriptors. And the maximum is, I'm guessing, 1024. It's quite a low limit to the number of the defaulted limit. I think it can be extended up into like 1 million or something. But the default setting for a typical Linux is 1024 open file descriptors. Off the top of my head, off memory, I know it's a low number. I don't know if it's definitely 1024. So once we've called this open function, we've created this file descriptor. We can then read and write to and from this file descriptor. Oh, we need to include the fcntl file control, and this will open our file basically that we've supplied. Whenever we do an open, we also need to pair that with a close. So later at the end of the program, at the end when we've done our copying operation, we want to make sure we close that at the end of it. So let's check that works. Implicit declaration of close. So in order to use close, we need to include the Unix standard library, which we'll come to in a second. We're going to need to make a file to copy, aren't we? mvim test.txt. Let's do this. Is a not doing it in capitals. This is a test. This is a test. We don't need to do a massive file, do we? LPC test, and we're going to have to supply an output file, even though it's not going to write to it. And yeah, the program works, and it doesn't crash. So we're opening this file, so we're not actually doing anything with it, are we? So let's do something with it. What we need to do is we need to read the data from the file. We'll start by just printing it out to the standard out. So we'll get this program to read the data from the file and print it out into onto the screen with a normal printer. So let's start by doing that. So what's this read function all about? So this, as I've just said, is included in the Unix standard UNI std.h, which includes Unix specific commands like read, write, pread. There's quite a few of them. Some of them are quite unusual. Windows, we obviously have a different read write kind of paradigm. I'm just covering the Linux one here for the time being. It certainly won't affect our neural network implementations. Although we will need to be able to save our trained models to files and that kind of thing, we can build a cross-platform implementation by then. We'll just do the Linux one for now. So read, we've got a file descriptor. We've just created a file descriptor. We need a buff. We need a buffer to save our read data into, and we need a number of bytes we want to read when we do this. When we make this call. So we need a buffer before we do our read. So we need a car buff, which is going to be an array, and let's make it the size of buffer size, which we'll define up at the top here. Define buffer size and make it 1024. As a good hint, as a good tip, we should always make, in fact, pretty much always make a buffer size for reading in files multiples or divisions of 1024. So 1024 times 32 for 32 kilobytes. It's a convenient size for reading and writing. It allows the operating system to optimize the kernel to optimize the read and writes. It makes the program a lot more efficient. If you have an unusual size like a buffer size of 37, it's an unusual size. It's difficult to line that up and do any alignment with it. But 1024 or multiples of it are very handy, a convenient size for the operating system. So we want to read our file descriptor. We want to read into our buffer, and we want to read the amount of bytes buffer size. Now it doesn't matter if there's not 1024 bytes, because we'll read up to the buffer size on this read function. We don't have to guess exactly how many bytes are in the file and then make the buffer size exactly match it. We'll just read up to the buffer size, and when we do call this read function, it will return the number of bytes read, which is handy because we're about to print them out now. So we're going to make a for loop. I is less than bytes I plus plus, and we're just going to print out, we're going to cycle through the buffer and print out a character for every position in the buffer that we have a byte for. So this is a test. We output the contents of the file, and we can prove that this is another test. But we don't need to recompile, do we? And now we print out both the lines, so we can read our file. But what happens if, so we've got 1024 buffer. So if we do YY 100 200p, how big does that? So that makes us 3000 kilobytes, and our buffer size is 1000 kilobytes. We cut off halfway through, don't we? We cut off halfway through. So our program so far at copying this file, we aren't copying a file yet, but we read 1024 bytes and the program quits. We don't want the program to work like that, do we? We want the program to read any size of file. So we're going to have to do some fancy while loop action. So we're going to have to while through until there's no more data to be read. And we can use this byte as a condition for the while loop. So we can do, for as long as this bytes is not 0, there's more data being read, and we can perform an action. But as soon as there's 0 bytes returned from this read function, we can consider that file to have been finished and then just close it and exit the program. So we need to do, in fact, let's do int byte. Let's make that outside the loop, and we're going to do it. We're going to put this in a while. So we're going to do while bytes is not equal to 0. We have to make sure we wrap this whole thing in parentheses, otherwise we're going to be evaluating something entirely different. And let's put this, just to confirm everything's working, let's put this inside the while loop, and we're caps lock. And now we read to the end of the file. We don't cut off halfway through a line. We read the full file. We could output that to out.text and just confirm. So we've got 201 lines. And, well, yeah, 201, 202 lines. We've got the spare line at the end. We make an exact copy of that file by piping it with the output. But we want our program to actually do the write. So rm out. So instead of outputting to the screen, what we want to do is we want to call the sister function of this read, and we want to call write, don't we? So let's get rid of that altogether. We want to do write. But we need to open another file, don't we? We need to open the second argument as the file. So let's do that. So we want an FD2, and if we're calling an FD2, we're also going to want to close FD2. Now this time we're opening argv2. We're opening the second argument that we've supplied the output file, and we don't want to open read only, we don't want to open write only. Now you might think that's enough, we can just crack on with running this, but actually that's probably not quite enough, is it? Because we also need to have o create, and we also need to have o truncate. So what does truncate mean? Truncate means if the file already exists, we just zero it. We just remove any content. So we just overwrite. We're making the default operation for this program to be an overwrite. We can obviously we could specify flags in our the way we want the program to operate. But as a default, we're making it so it'll overwrite. It'll create and overwrite the file if it doesn't already exist. If it already exists, it'll just overwrite it, just like the actual CP command. But we also need a node this time. So going back to the very start of this video, we said we had an inode. An inode has permissions. So when we create this file, we need to sort of let the it needs to be created with some default permissions. Otherwise, it'll just have no permissions. So we want to do stat underscore inode read user. Very difficult to remember that. Stat underscore inode write user. We can also do write group grp and write other OTH and read other and so forth. But stat, anything, whenever you hear the word stat in system level C programming, it's got something to do with files and directories in the file system. It stands for inode, and then this is the flag. Now we separate these with when we have multiple flags, we separate them with these OR symbols, because this is a bitwise OR, and I probably won't cover them in this part. I think we'll just make a copy. We'll make our write command work. So we've got our file descriptor for our open output file. So we just need to write to that, don't we? So FD2, this signature is almost exactly the same as read. So we read to a file des. We have a buffer and we have a number of bytes that we want to write. So it works exactly the same way. Buffer, and this time instead of reading 1024, we only want to write the number of bytes that were read. Kind of makes sense, doesn't it? And this will now probably work unless I made any mistakes. No, I haven't. Test out.txt, and we've got a copy of our file. Nice and simple. And it is 200 lines. We've copied the entire file. So that is how you make the copy command in Linux. It's a very Linux specific part, this. One thing we want to do is we want to add some error handling. Let's do that before we wrap up this video, which has been a bit of a long one. So if we include error number.h, which is a library that deals with error numbers. Let's leave it at that. So basically, if this read function, if it returns a -1 as a condition, then an error has happened. So we can catch that. So we can do if byte equals -1. And we've obviously got an error situation here, haven't we? So what do we do if there's an error? Well, some errors are more critical than others. And there's one particular error where we can just ignore it and carry on. And so if we do if ERRNO equals EINTR. So if the read was interrupted by another process, if there was an interrupt signal received, we can just carry on. We can try again and try again and try again until that interrupt signal is no longer there. To go through signals is quite a big topic, but basically any program can be interrupted by the operating system at any point, or by a user issuing a command or something like a Control-C. There's various signals that happen. Sometimes a program is stopped because a really high priority thing's happening somewhere else in the operating system, and it'll send an interrupt signal to the running process. So the schedule will just change which process is being run. If that happens while this is being read, we can just try again in a second. So if error number equals EINTR, interrupt, we can just continue. No bytes have been read, so we'll just go around again and try again. Else, for all the other errors, we want to break, and we also want to print out an error message. fprintf error read failed. We also want to print out an error message. We don't want the dot at the end, do we? And we want to put that in a new line. So we can handle the EINTR, any other type of error that would have happened while reading. We can't really handle that, so we're just going to exit the program. And because it's not a long-lived process, I think that's a reasonable thing to do anyway. It's just issue a message saying the copying's failed. The write, so this doesn't fail. You can consider a write operation to not fail. Obviously, there's reasons why it could fail. The power could be cut from the computer, but generally writes are buffered, so this write won't happen instantaneously. The kernel sort of stores them up and writes them at a convenient time, so it won't instantaneously write. But if another process tries to read from this file that we've got open after we've done a write to it, and that write hasn't been committed to the file, then the kernel will flush that write to the file, and then the other process will read the most updated version of the file. There's a whole lot of complexity to synchronizing files, especially with threads and multiple processes, and the kernel is very, very clever in this respect. So that's basically how we make a copy program. So let's neaten this up a bit. So let's review that copy program. So we have a main function which we're passing arguments from the command line, and we're doing a quick check saying that if we haven't got 3 arguments, we're just going to cancel this program. We're going to print out an error message and then return -1 and end the program. But assuming that is the case, then we're going to open our file script. We haven't actually checked if errors here. We have to do a lot of error checking for if we're working with files and strings. Lots of error checking. If fd equals -1, I'm sure this returns -1 if it's an error. Command to open. What we're checking, return. I don't do a huge amount with files, or at least I haven't lately. I'm sure it returns a -1. If the file it doesn't open. Let's have a look on internet. C open return value error. The normal return value is non-negative. Yeah, so the value of -1 return this side. Yeah, so a file descriptor has to be a positive integer. So, and we have some reserved cases for file descriptors. We've already encountered the standard output, and we've got the standard input and the standard error. So the standard in 0, standard output 1, standard error 2. They are file descriptors that every process has. We can close them and then not be able to use them anymore. We can run a close on the standard out down here if we want, which would be a very unusual thing to do. So we need to handle these errors. So if fd2 equals -1, we want to return -1, and we want to print out an error, fprintf So the stderr, that's going to file descriptor 2, which is stderr is just a mapping to 2. And we're going to print out error, failed to create file. 2yy, failed to open file. So going back to our review of this program, so in FD, open argv1 read only. So we're opening the argument that we passed as argument 1 with the open system call and creating a file descriptor called FD. And then we're creating a file descriptor 2 where we're opening the second argument that we passed, although it's technically read as the third argument, the second argument that we passed, not the program name. And we're opening it with the following flags: O write only, O create, O truncate, and then we have mode, stat, inode, read user, stat, inode, write user. So we're having those permissions when we create this file, and we're having a default behavior to just overwrite the file. So which is the same as the copy command, and we can make this program more complicated and change that if we want to. And then we're creating a character buffer of buffer size, which we've defined up at the top, which is 1024. And then we're creating a variable called byte, an integer, which we're going to use to record the number of bytes read when we call a read function, which is defined in the Unix standard header. And we supply the file descriptor, the buffer, and the maximum number of, well, the size of the buffer, the maximum number of bytes we want to read. And as long as that's not equal to -1, we drop into this while loop. We check the error, make sure it's not any interrupt error. If it is an error, if this read returns -1, there's been an error. If it's an interrupt error, we just continue, and the continue command will just carry on. We'll go back around this while loop again and have another go. Else we quit out the while loop, print out an error message, quit out the while loop, and close the program. Assuming there's not an error, we write to file descriptor 2. Whatever's in the buffer and the number of bytes that were read. So if we only read 2 bytes, we'll only output 2 bytes. And then we close the 2 file descriptors and return the program to the operating system. New.text. And the program works like so. It will print out. I don't really like that the example we've got is just the same thing repeated over and over again. Let's copy the source code. Copy.c. Oh, lpc copy.c. Didn't know how to use my own program. We've now made a copy of the program we've just written. Very clever, eh? That's what it's all about. So we've made a program, and now we've copied made a program that copies, and then we've copied the program. Some kind of strange Inception style paradox. And that about does it for this video. This is a bit of system level programming, which we are going to need to be able to handle files. Now, usually we would use the fopen user space file opens. Going through this way of doing it, we're dealing directly with system calls, and we've obviously had to cover a little bit about, certainly with stat, inode, read, user. Understanding these flags are really important. Any function like fopen is just a wrapper for open, and fread is just a wrapper for read, and so forth. Or basically built on top of that kind of infrastructure. So it's important to know the underlying infrastructure, I think, anyway. And as everything in Linux or Unix-like operating systems is a file, right into a network connection works exactly the same way. We have a socket descriptor, which is basically a file descriptor, and we have a send and receive, which is basically a read and a write, and we send and receive a buffer and a number of bytes, and receive a buffer and a number of bytes, receive into a buffer and a number of bytes. Works exactly the same way. This paradigm is used throughout all file handling, and as everything on Linux is a file, it's used for any kind of stream. We call them streams, any kind of stream. Or block storage, which is really good to know. All really good stuff, I think, anyway. Make yourself a copy program, and make sure you handle these errors. Make sure you do this bit. It's really important to include error number, error num, and to check that the read wasn't just interrupted, otherwise quit the program. You can obviously read about this error no style. I mean, I'll cover it in more detail in this series, but if you want to jump ahead, you can read about this on a quick Google search. Because there's tons of these EI. Can we just do a man page for error number? Yeah, we can. We got a list of them all. There's tons. E8 access permission denied. These are all sort of system level errors. Bad F. This is for a bad file descriptor. And this error number header has all these things mapped, so we don't have to write a load of infrastructure every single time we want to handle an error like this. We'll try our copy program with a massive file. I haven't got any massive files. It's the biggest file I've got on here. I haven't got any big files. I could download a massive file, couldn't I? Large test file. Let's download a Vodafone very large test file. Gigabyte. That's too large. My internet. I've seen how slow my internet connection is. It's horrendous. 10 megabyte. That'll do us. 10 MB.zip. MB. So these are the same test.zip. Exactly the same byteage. I got unzip installed. Unzip, zip, extract. How do you use unzip? I don't intend to zip things. List files. I'll do, don't we? That's not working because it's not a zip file. So has our copy not worked very well? Oh, it doesn't work with the original one. End of central directory signature not found. Either this file is not a zip file. So what have I downloaded here from Vodafone? Why call it a zip file if it's not a zip file? I think this is another story for another time. These files are made of random data. All they're listed as zip files will appear to be corrupt if you try and open them. Right, okay, fair enough. What was the point in calling them a zip file? And why not call them a test file? Or a random file or something? Crazy, yeah? Well, we confirmed that it copied. Because we have a copy of our source code. Here's the source code to copy some source code. Right, I will call it. I'm really tired, by the way. I don't know why I made this video now. I'm absolutely knackered, but just in the mood to talk about programming and do some programming. I've been working on a lot of network sockets again. I've been doing TCP hole punching. Have you heard of TCP hole punching? I won't do a big explanation now. I think I will go through it because it's very much on my mind. I'll just well, assuming I can figure it out. I've pretty much got it working, but it's a difficult thing to test. I need to test it in the real world, if you know what I mean, to make sure that it actually works. It works in my sort of testing locations, sort of going around to somebody's house, or just going outside, or just connecting my laptop to my phone, you know, tethering, and then seeing if I can make the TCP hole punch connection. I'll talk about it another time. It's not relevant to this video, but files is because I've been doing a lot of sockets. We'll be doing a lot of send and receive. Right, I need to get cracking with this series. I need to get on with these making good parts. And to do this as a regular thing, as I keep saying, I'm going to make like 3 videos a week and then end up doing 1 in 3 weeks. That's about to change. That is about to change. If I can do this while I'm tired, then we can make a video every day, because do tend to work a lot. Right, I'm going to call it a day at that. Right. So that's how you copy files. There's a little bit about file handling to get the new year started off with a bang. Happy 2024, everyone. Right, I like finishing on the screen I started in. I shall see you next time. Goodbye.